Hello, everyone. Thank you for joining us for another live webinar session with EE Tech and All About Circuits. This session is brought to you by Vishay. My name is Jason Montgomery, and I'll be your moderator for this presentation today. Let me tell you a little bit about the session that we have coming up, and then I'll hand it off to our speaker. The name of this session is Energy Harvesting, Eliminating Battery Replacements for IoT Nodes. And our presenter today is Tassilo Gernandt. Tassilo has been a circuit designer for more than 15 years and helps customers to design, lay out, and debug circuits, including lab work and simulations. He's a field application engineer with Vishay and serves customers abroad. His background is RF and low-power IoT devices, and before he joined Vishay 2.5 years ago, he worked at an institute as a project manager and managing engineer. And everyone that's in attendance here, as you always have with the live sessions that we run here, there will be a live Q&A session that comes afterwards. If you look on your screen, you'll see a Q&A box. That'll enable you to ask questions that Tassilo and I will be going over after the session with some other experts as well. So with that, Tassilo, welcome, and I'll get out of the way and looking forward to the presentation.
Thank you, Jason. Hello, welcome everybody for joining our webinar on eliminating battery replacements. And Vishay has developed components and a harvester board with different supercaps to enable the thought for IoT, which is pretty much install and forget. You don't want to waste energy and time to do battery replacement. That's why everybody dreamed of something like install, forget, and last for more than 10 years. Thanks, Jason, for the intro. There's nothing to add here. A special welcome to Nanowrimox, which is a company who does a lot of development for us in supercaps. We have specialists in the background from supercaps, from opto, photovoltaic devices, and somebody for all the commercial questions, which can be dropped into the box anytime. Don't wait until the end, but of course you can wait until I'm done. So for our motivation, IoT lives from little tiny devices. In this case, the question is always, does the energy balance out? Because only then sensor would survive whatever condition, whatever, for longer periods. And the simple question is, what energy do we need? What energy do we get from the field? And to catch everybody's attention, I did some real quick mathematics calculation. A short-range device, IoT, would always, require the most energy from sending off data by RF. If it's one of the ones who's not a data logger. So the simple case of a package being sent off with 20 dBms, which is 100 milliwatt, for a short-range device, which would require only 2 milliseconds of a burst, you need 400 microcoulombs of energy. The sensor itself would do some periodic sampling of data and then log it or decide on a threshold and then send off data. This is typically lower, and then you always have the sleep and real-time current, real-time clock current of at least permanently 0.5 microamps. And what does that mean for the energy harvested? The minimum you need to compensate or to balance out 400 microcoulombs is min 2 microamps for 200 seconds. 200 seconds is a known value to still say an IoT sensor is alive, because it would always send alive messages if it's not the actual coincidence of trigger or passing a threshold. For the periodic sampling, you need another 1 microamp for 200 seconds, 0.5 permanent, totals up to 3.5 microamps. And with 50% conversion loss, this is always the case. Designers would always say, look, from conversion, from storing, from leakage, anything, you would have to have at least 7 microamps. How does that case look like for LoRa, which is the more known approach these days, because you want your signal to reach farther, which can be up to 1 kilometer. I did an example of SF8 spreading factor 8 here, which would require a 20 millisecond long burst. Same power, RF power, would require 4,000 microcoulombs. The rest is pretty much the same. And for a LoRa sensor, also because of the spectrum usage, you might not be able to transmit that often, but every 10 minutes, is still a known value here. Every 10 minutes means 6.7 microamps for those 600 seconds harvested. The whole totaling up to 8.2, conversion loss 16.4, and we will come back to this number at the end to compare really what can we harvest with our tiny pin photodiode. So here's an overview of the board. We have developed a board that's called V Harvester. We have 4 key building blocks. I named them source, PV cell, a controller converter in the middle, a supercap up here, and an interface to attach any kind of sensor, RF, temperature, humidity, proximity sensing sensor. These are the normal use cases you have in IoT. For the motivation, it can be split up into 3 simple building blocks, which is source, storage, periodic task. I included some IoT node examples down here. You either have an obvious antenna, sometimes it's integrated here on a PCB, and sometimes it's inside completely enclosed. The 4th block is always the controller, the optimizer, the maximizer, and supervisor. And with EPs, which is a cooperation partner, we found a company who can deliver pretty much exactly what we need in combination with what Vishay can deliver. Vishay has lots of passive and active and semiconductor components, and I will include and mention a couple of them during this presentation. Everybody knows the possibilities for harvesting. I'm sure you've heard of radiation, photovoltaic, RF radiation. Thermal would be a Peltier element. For mechanical, it would be a piezo element. And for a battery, it's typically either a battery, a capacitor, or a primary cell attached. On the right, you always have sensor sampling, storing data, and transmitting in a sensor that is includes the brain pretty much. The challenge has always been, IoT has been around for a couple of years, at least 10, I'm sure, has always been not enough energy, or the energy is not anymore as much as it was in the beginning from, say, dirt or aging. Battery capacitor in the middle is always about the capability, storage capability, the drive capability, if we then need some current, and the self-discharge. The right side, of course, the challenge is about too often, send off too often, or the peak current is too high, and that's what we're trying to address with our solution here. And there's challenges on top, which is especially for the batteries, the temperature limit. And then, of course, the voltages never fit. For the PV cell, it's typically 0.5. For RF, it's very low. For thermal, it's very low. And for mechanical, the piezo element delivers a high voltage. First have to convert it. So it's all about the losses from conversion. And then, of course, everybody knows when I need it, it's discharge. When I take it out of my drawer and want to use it, it's discharge, like my, drill at home, electric drill. And you have to charge it. So, and then the last challenge is, of course, as I mentioned, aging or degradation. How good is the whole design after a couple of years? So here come the solutions. We include on our evaluation board the PV cell, 3 times in series, each of them 5 by 4 millimeters. It's a reflow solderable one. It delivers open source voltage up to 0.5 volts, direct sunlight up to 2 milliamps, more than 13% efficiency, and we'll come to this calculation later on. In the middle, the Supercap, which is our AnyCap, Vishay's AnyCap technology. We integrate a 4 farad version on the board to really show, look, the smallest cell can do the job. There is larger versions. All of these were tested up to 35K cycles, which is a lot. It's not comparable. It outperforms lithium-ion batteries. It has a very low leakage, and we have an upcoming SMD version, which is reflow solderable. We try to build everything on a platform character. We have an interface which can actually enable or disable an additional voltage, and we have a health indicator. The solution to the other challenges, sensor enable, I mentioned that already. We include a low-loss inductor core. We have our Vishay's IHLP inductor technology with soft saturation. We have integrated, or we enable here a solution, if not used, to still have 60% of energy remaining after half a year with our Supercap. The solution in more detail. So we'll look at the PIN photodiodes, which are the tiny PV cells, photovoltaic cells. In our data sheet, you would see only numbers which are lower than direct sunlight or lower than, say, office light. One example here is it's a blue enhanced version, which works actually much better towards UV light than any other standard silicon cell. At 950 nanometers, it would deliver short circuit 50 microamps, an open circuit of 350 millivolts typically. And I can say it's good to use at least 2 of them for being close to about a volt, half a volt, and a volt. We've done some measurements with the PIN photodiode. One was an LED, which is a dimmable version, you know, from your ceiling. It's a light bulb which is dimmable, and here you can see, you know, if the lux number is higher, then of course the current goes up, the delivered current. 4,800 lux and 120 microamps was the maximum here. If you expose it to direct sunlight, the curve looks a little bit different, but goes up higher. The maximum would be actually higher than the 600 microamps you see here for real direct sunlight with no pane in between, glass pane in between. You would go up to 2 milliamps. Then we have in the middle of the brain, the controller, the converter. This is from our partner, EPs. It actually allows a cold start of the whole system because it starts to work from 3 microwatts on or 380 millivolts. And I tested it even with 1 PIN photodiode that it starts up nicely. The cool thing, or the, say, smart thing, is actually that the controller would deliver always a standard 1.8 volts or something between 1.2 and 1.8 volts. Typically, it is 1.8 going out here to keep the controller running. And then the controller here, the attached interface sensor, could enable this additional voltage with more current to say, I will power now a sensor, I will power my RF part to send off data. And that's really unique and new. It includes maximum power point tracking. It has a balancing input to balance even the charging and discharging of the Supercaps. It's a 5.5 millimeter design. A 2.2 millimeter version is just coming up, as I understand. In the middle, you need 12 by 12 millimeters total size. And now we will come to the Supercap in detail. We integrated the 4 farad 4.2 volt version. It does a direct replacement of lithium ion 4.2 volts, and that's what this board is about, to replace the 4.2 volts, because we will compare this on the next slide with the performance of lithium-ion batteries. In general, these cells are stackable. 3 of them, 3 times 1.4, end up at 4.2. There's many, many more versions to whatever is needed. There's special embodiments with cable, with plug, and now you can see the total size here, 60, 150, and 60 square millimeters. So the total would be around 300 square millimeters as the minimum to build such a circuit. On the backside, we will have additional SMD solderable any caps. These are EDLC versions. They are nominal at 2.1 volts, and again, 2 in series. You always see those in series, or even larger version, which is under development. In series would again add up to 4.2 volts, which can again replace a lithium-ion battery. The first version has 0.2 farad. It has a low leakage of, our data sheet would always be very conservative and claim 5 microamps, which is over the complete temperature range, which is up to 85 degrees Celsius. Vishay has done some measurements already, and it shows a nice 0.5 microamps at room temperature. And of course, you see a couple of MOSFETs for very nice isolation on the backside of the board, or to enable or disable the additional voltage. Now comes the solution to the challenge, drive capability and high peak current, because everybody would say, well, it's a tiny device, but can it actually drive a lot? And it can. Vishay attached this little supercap, the smallest one, 4 farad, to an IoT sensor, which would transmit data, which is the highest challenge actually, transmit RF data. And here you actually see the voltage drop at the supercap. You see the on-off keying signal here. After that, a reception slot, a little one here. Then an FSK signal, which is number 2. Then again, a little after that, the reception slot. And then because it didn't receive an acknowledgement, it would try on the next modulation, which is the high power LoRa SF7 in this case, spreading factor 7 burst. And again, you see the reception slot for the acknowledgement. At the lower graph actually only shows the RF power detector to show, that the RF output is constant. The voltage drop shows 0.7 volts. This actually indicates an ESR of 5 ohms. What you would see in our data sheet would be 22.5 ohms, which is again conservative. This was done at room temperature, and it works nicely. Next challenge, enough energy after some time. So what about aging? Does it still have enough? Our HVC 169, which is the blue version which we saw, has 50 watt-hours per kilogram, which is comparable to the lower end of the lithium-ion batteries. And those lithium-ion batteries have typically 1,000 cycles and 50% remaining. Our supercap was tested 35,000 deep discharge cycles, and we still have 90% capacity remaining. I'll show you some more details on the next slide, which is the test we've done. So we have, Vishay has done a test or a deep discharge every 5 minutes, which was charge 300 milliamps, discharge 90 milliamps. It's actually a higher power version, and it was close to a cell phone, powering a cell phone. And then Vishay did the characterization every 100 cycles to really see how much capacity is left. So we have a really nice cycle stability and almost no aging. On the other side, self-discharge. I mean, how can that be? It's small, it has a lot of energy, it can drive a lot, and still have a low discharge. It's just a nice part, I would say. What we claim or what we measured is at room temperature and leaving the unused, it's actually better than this year. After half a year, we would still have 70% remaining, more than 60%, and actually 60% after a complete year, which is mathematically a leakage current of only 0.14 microamps at room temperature. Here's the block diagram of the key components, which is the energy harvesting element down here in the middle of the controller, the capacitor, and Vishay has many different other sensors which can be attached on one of those interface boards. There's more components on the board. There's a buck storage inductor, IHLP 1008, which is a really small version. It actually goes up to 2 amps or 8 amps, depending on the value, which is a little over, but, then the loss is low. And, of course, an IoT sensor would always require a voltage divider to measure its health status. That means it has to measure the voltage at the input, maybe at the output. And, of course, everybody is looking for something that is stable, and we integrated a thick film 0402 1% resistor with a very high ohmic value of at least 20 mega ohms, and that results, because it's a voltage divider of even higher resistance, of less than 0.1 microamps required only to do those measurements. The other nice low power device would always be a back-to-back isolated MOSFET to really isolate circuits from each other. Blue enhanced PV photocell we mentioned already. And here on the right, you see an additional Supercap from Vishay. It's an EDLC which can drive more current. It's actually rated at 3 volts. So if you have a 3-volt design, this would be the choice. Or if you ever integrate something into a tube or a battery cylindric cell, then a 10 millimeter version might be the best choice. It can drive more. The leakage is a little higher, but still after 3 days, you would still be able to use it. All right, and a couple of key components from the schematic. We also integrated on this evaluation board a USB port to charge it and to have that health indicator activated. It can actually be bypassed also, but we know, or I know, the challenge of saying, look, if I have something blinking all the time just to show me something, it would always consume energy. So why not disable it? So once you plug in your USB, you will see the blinking health indicator, but of course you can also bypass that. 3 photocells up here can be shorted to go even lower, 0.5 volts each, and the many different choices down here, jumperable or even attachable at a different header. And then the platform character of the interface allows to attach one of our sensor boards. We have at least 3 low power devices on one of those attachable boards already. They are typically proximity VCSEL sensors, and they can detect up to 2 meters. I think the first 3 versions we have on those boards detect up to 30 centimeters and work down to 6 microamps at 3 hertz sampling rate. That means 3 times a second you sample and would actually be able, with 6 microamps, be able to detect whether somebody is in proximity, whether a box was opened, whether something in the surrounding has changed, and then of course, the IoT sensor would wake up and either log it or send off the data by RF. What's nice about this interface is the low voltage out is always there, which means the microcontroller or something here would always work, and this sensor could enable an additional higher voltage, which is modifiable. Right here, you see 2.5 volts, but it could be anything between 2 volts and 3 volts or 3.3, to then be able to do, to match the sensor you're actually sampling. All right, and now we come back to the challenge of the first slides. You saw that we need at least 7 to 17 microamps of energy. I included 2 pictures. One is more like an LED office environment where you have a lamp. On the right, a more, the sun is shining into this office. And again, you can say half a day of harvested energy would require an additional, doubling this value. So the total you need is 14 to 34 microamps. And we've done measurements with the lux meter and saw that at 600 lux, which is a normal and nice, bright, surrounding, our pin photodiode would deliver 14 microamps. And if it's more sunny, it's actually pretty bright. 1,000 lux is still reasonable because direct sunlight is above, I think, 100,000 lux. You would still, with the 1,000 lux, you have 34 microamps. And then we can do some mathematics on the efficiency calculation. That means the 2 numbers here, 29,000 or 1,000 lux, actually means with a conversion of 126.7. If you go over the whole spectrum, I've heard this number is actually 134 instead of this number. Then the incident power on the 7.7 square millimeter cell would be 1,765 microwatts. Output being that much gives an efficiency of about 17%. At 1,000 lux, it's actually better because it's a low light optimized design. It would be 61 microwatts incident, about 11 microwatts output, and 18% of efficiency, which is close to what 20% you always see in silicon photo cells. All right, here comes the summary. We integrated, Vishay designed a nano power photovoltaic energy harvesting with any-cap supercapacitor. Nano, it is there for a reason, because all components have been designed to be better than microamps. Okay, all components can work below 1 microamp to really last very long. We integrated 23 square millimeters of photocell, dark light optimized, up to 2 milliamps max. It includes a maximum power point tracking and a controller that does balancing on 2 cells, for example. We integrate ultra low leakage back-to-back MOSFET switches for extreme low reverse current. We integrated an IHLP power inductor for lowest loss conversion. The whole design is an enabler for design for designs who's supposed to last more than 10 years. Lowest leakage, efficient transformation and storage. And I included in the PowerPoint, which is available for download, 3 links. About a year ago, we started this install and forget thought or design. It includes many, many more components which are suitable for IoT. For example, a wireless charging coil or a low leakage tantalum capacitors. And there's also some more explanation and lists for what components you could choose, and a link to the Sensor Explorer boards, which are the ones I showed on the slide, the last slides. All right, thank you. If you have any questions, feel free to write them. And now, Jason, I think we can go back to the Q&A.
Great. Thank you, Tassilo. Everyone, this is Jason Montgomery again. Can you hear me okay, Tassilo?
Yes, I can.
Perfect. So everyone, thank you. I'm seeing some questions that are coming in here. And as a reminder to everyone that's in attendance, we do have time for a live Q&A here after the session. One of the questions that I will touch on just really quickly is link for downloading the slides, which you'll be getting the most recent version of this slide deck in an email that'll come out to you as a thanks for attending. And there also will be an on-demand version of this webinar for people to view this again as they need. So everyone, you will be able to get those slides in a follow-up email that'll be coming after this session. And with that, Tassilo, let me start digging into a couple other questions that I'm seeing here. And I know that we have some other people on the line that you might be deferring to. Feel free to just introduce them and hand off the questions as you see fit. The first question, Tassilo, is, will this design be available to customers?
Yes, it will be available. Our plan is to, right now, we have 100 boards being qualified, and we'll release those in January 2022. It should be, we plan to have it available through the known distribution channels and for some dedicated designs and customers. We would have those at Vishay for evaluation.
Got it. Thank you. Another question that I'm seeing here, what's the smallest cube you could build with the suggested components?
Mm-hmm. Well, let me go back real quick to the square millimeters which I've shown here. So thank you for the question. It all goes back to the thought of smart dust, and the smart dust is always the smallest cube, which includes a storage element and a harvesting element and the brain. And you can see here actually a 4 by 5 millimeter PV cell, and I would suggest to integrate at least 4 on the top side. If it's a cube of equal size, that would mean 10 millimeters by 10 millimeters for the PV cell on top. And because within the 10 by 10 millimeter cube, also the Supercap would fit, just as the other components if you do a smart layout. That total should be 10 by 10 by 10 square millimeters total. As a little nice cube, which is very small.
Mm-hmm. Perfect. Thank you very much. Another question that I'm seeing is, how do you get a visual response that the device is working?
That's actually something I tried to explain already. I can say it again. This is actually the two health indicators here. I said you can bypass this requirement of having the USB attached to it to enable the little LEDs. But of course, all designers require, or the attached board would require something periodic, like a live signal. And of course, the visual thing is nice to see something that's flashing very short, like bick, bick, bick. And that's implemented with a green LED. And like I said, it can be bypassed, that it would still work without USB.
Another question I'm seeing here, Tassilo. You mentioned sensor explorer boards to attach to the interface. Which ones are readily available there?
Sammy, are you on the line and ready to answer those questions? If not, I can say one of the slides actually shows one implementation, which is this one here, and we have 2 other versions for low power. There is many more. All of them have the I2, or many of those have the I2C interface already on board, and this actually goes would fit with the future version of the EP's chip, which is also an I2C version. Then you don't need any more all those resistors. The resistors are there to configure the voltages, like a threshold or stop charge. Here are a couple of resistors which can be changed. In the future version, this would then be handled by I2C protocol. But for this implementation, the whole thing is a hardware-ready design. I know the pain of, if you get an eval board and you first have to do some I2C programming, oh, come on, it doesn't work. So we really thought a simple version, which is ready to use, is the best choice for the beginning.
And it looks like we might have, Sammy, can you hear us okay? You might be muted, Sammy. All right, sorry about that. We will continue with a couple other questions here, Tassilo. We might be able to get Sammy on to speak a little bit to that as well. Another question that I'm seeing here is, I work in the hydraulic valve industry, cartridge valves to be specific. Do you have any lead users of this technology yet in mobile industrial hydraulic space?
Yep, this is Norbert speaking. I have answered this already online, and we have no experience, but basically we have experience with supercaps in water faucets, operating valves for safety, close down with medium turbines to charge the supercap.
Thank you very much. Another question here, and we can defer this question if it's not one you're ready to speak of, but we do have a question on the estimated cost of the application here.
Of the application or the evaluation board? The application would require, I think, 2, 3, 4 PV cells, a controller, and the supercap. I don't know an estimate yet, but I think those 3 components were always targeted to be $5 or something for an IoT sensor. But I'm not sure.
Okay.
Gerald, do you have more thoughts? We have a specialist from the Supercaps online.
Yeah, for the supercapacitors, and of course we're in a range of a couple of dollars. And the idea would be as well to provide this tool or this board, let's say, and as an engineering tool. And of course, as Tassilo already mentioned, in January we will be fixing this, and then we can send it out. And then we will of course promote this, and then you can buy it on the catalog houses mainly, and get these modules from this site.
And if the question is about what, okay, and if the question is like what's the evaluation board's going to cost? We don't have a fixed price yet,
okay.
But it might be between the $50 and $100 somewhere.
Correct. Yes, we have to fix it on that one. So think about on between $50 and $100 each.
Got it. Thank you very much. Another question that I'm seeing here. So far, what is the best source of energy for harvesting?
The best source is actually PV in general, if it's outdoors or somewhere where you have light. There is a lot of dedicated designs where, for example, close to a hot tube somewhere, you would have enough power. I know a couple of Fraunhofer designs who actually attach something to pipes to harvest energy. You always need a big backside that is the heat sink on the cold heat sink on the other side to have a delta and keep a delta. So thermally, I would say it's possible, not the best. The piezo itself, the piezo element would deliver a high voltage, which is nice. Then you only need a down conversion. Still, it requires a permanent vibration somewhere close to a motor that might fit. And then RF-wise, 10 years ago, I already worked with a university on harvesting energy from wireless LAN routers. And the more repeaters, the more devices you have in your house, you can actually harvest something close to minus 10 dBMs, which is like 2 meters from a router. From EPs, there are different chips dedicated for those harvesters. And I can send out links, or we can talk about it afterwards to maybe find a solution for RF. I would say the next one is really RF because we are surrounded by so much radiation, wireless LAN and 5G and so on.
Another question here, and this looks like it's a series of nestled questions. I'll read off the whole thing, and then Tassilo, we can break it down as we need to. In the light example, what's the average lux needed during a day? For an office at 600 lux, that's very bright and would be on for 8 hours a day. You mentioned charging for half a day. Will the application drain the supercap over time, or will it still charge? Do you have to pre-charge the supercap at the beginning? So I know that there's quite a few questions there, but specifically about draining the supercap, pre-charging, an average lux needed per day.
Okay, first of all, I want to say there is, of course, an isolation. You wouldn't discharge from dark light. 600 lux is bright. I know some engineers work at 200 lux. That's correct. Then you have to do your own mathematics. 1,000 lux is actually hospital inside environment. 1,000 lux. Yeah. But you can do your own profile and say, look, the sun is shining for at least half an hour, and do the mathematics and sum it up. What the controller would do, or the health indicator that is actually provided, helps to say, I will skip one of the RF bursts to save power, because right now it might be cloudy for 3 days. So depending on how much you harvest, the design can actually, or the brain, the controller, or the sensor itself can say, I will not drain more than I get. I hope this answers the question.
Yes, thank you. And another question here, since you just mentioned in this Q&A 5G, a question is, there are plans for harvesting energy from 5G radio. Are you working on this? And would the harvested energy be near the numbers shown in your presentation?
I don't think it's going to be close to PV, to light. Okay, and I forgot one question from the last one, but I'll answer this one again. Okay, I forgot the last question ended. Does it require the supercap to be pre-charged at the beginning? And I showed you when the chip from EPs actually starts. It starts with 3 microwatts or 380 millivolts, and once you enlight one of those, or have enough light, it will start. Okay, I hope this answers the last of the other question. Okay, 5G radio and radiation. I have been working in the past on a couple of projects, EU funded, with some really big institutes who are working on that. 5G, it would require a 5G router at home to harvest enough. Otherwise, I would say 2.4 gigahertz or 5 gigahertz wireless LAN is the use case to try. We are not currently working with anybody on this. 5G, a link to 5G I can give you. Vishay has been working with a customer in Turkey to build exactly that design with more PV cells and a supercap to send off data to a 5G network. So it's not real connected to harvesting from 5G, but it's of course linked to 5G. So I know how much power is available there. 5G is not really high power. It's more like LoRa. It's, with the spreading factor, you cannot harvest that much. But to finish that story about RF, when we had the 2G cell phones around, everybody could buy those little tiny stickers, which you could attach from the backside of the cell phone, and they were blinking. So it actually showed you how much energy goes out that antenna. And when we had 2G, we still had lots of power available because it was really close to 2 watts you would send off. Right now, LoRa transmits at 100 milliwatts maximum, 5G 27 dBms, which is half a watt. So it's not anymore that much.
Got it. Thank you, Tassilo, very much. Everyone out there in the audience, it looks like we're through the first batch of questions here. We do have a little bit more time, so if there are any other questions that come to mind, this is a great chance to submit any other questions you might have. And Tassilo, while we give the audience a moment to submit any other questions, is there anything you would like to touch on again here, reemphasize or revisit from the presentation?
What I forgot to mention at this slide is actually, I wanted to say we have 29 different versions of only this size. That means the sensitive area 7.7 or 7.5 square millimeters. And we have actually 29, Vishay has 29 different versions. Some are blue enhanced, some are infrared enhanced, some have a filter on top only for infrared. We have only ambient light sensors with I2C. We have so many different versions. Please go online and check out what fits best. Also have some smaller version if you want to go even lower in consumption.
All right, I've got one more question. It looks like Tassilo that's come in here. Talking about the environment you might be putting this into. Considering if the device is in a working environment, what are possible trade-offs, these word shortcomings? Is there anything that needs to be taken into consideration, particularly for the environment that it's being placed into?
Well, in order to work continuously, you need some brightness. Otherwise, I don't think there's any shortcoming. If you design an IoT sensor with whatever you saw, please keep in mind you need space for an antenna to be able to send off data to somewhere. Many designers, came to me a couple of years ago and look, this is the sensor, and we have the housing ready already. And I asked, where's the antenna? We need antenna. Because if you can only send off to your next wireless LAN router, which is 2 meters away, it might not be sufficient. So, yeah, that might be something to consider. Keep space for an antenna. Keep enough light shining in from the outside, or keep it close to wherever you think it's bright. And then the IoT sensor would work forever.
Got it. Thank you very much, Tassilo. Well, everyone, I think that we have gone through what looks like it was a very engaging presentation and Q&A session that's followed afterwards. A couple of things to wrap up here. For everyone that's in attendance, you will be getting the most recent version of this slide deck emailed to you after this session as well. Thank you for joining us for this live session. You will also be able to access everything that we've talked about here on demand on allaboutcircuits.com in the industry webinars section of the website. This is certainly not the only webinar that I've had the pleasure of moderating with Vishay. If you go to their company profile or go look through the industry webinars that are there already, you'll find several other Vishay webinars that I would strongly recommend you go check out as well. And with that, Tassilo, I want to thank you very much for joining us today.
Thanks, Jason. Thanks to everybody who was online.
To all of our experts who are on the line here as well, thank you for joining us. And most of all, thank you to everyone who's taken their time to join us for this session here today. I am Jason Montgomery with EETech and allaboutcircuits.com. And then we look forward to seeing you at another live industry webinar again sometime soon.